In this video, we're going to look at some more conceptual examples involving the concept of linear independence. So the first example, this is actually example 3 because I'm continuing my numbering from the previous examples I've looked at in the videos for this section. So the problem is, can a set of 4 vectors in R3 be linearly independent? So if yes, then give an example, but if not, explain why. So at this point, I want you guys to think about this for about a minute. So pause the video and think about it for a minute. 4, 3, 2, 1, pause the video. Pause the video and think about it for a minute. Okay, so hopefully it's been about a minute for you. Just a few seconds for me though. Okay, so let's start to talk about this. So before I say what the answer is, let's think about this. So there are 4 vectors here. So let's just call the 4 vectors something. Let's call them v1, v2, v3, and v4. So let's let these 4 vectors be in, so our vectors are supposed to be in R3, which means they each have 3 entries. So we know from our previous videos that the way we check for linear independence is we put the vectors into a matrix as columns, and we look to see if there's a pivot in each column. So let's form a matrix that has these vectors as columns. So I'll call it A. So A has column vectors v1, v2, v3, and v4. Okay, so what's the size of A? How many rows does it have? How many columns does it have? So this is A, which is, well, I definitely know it has 4 columns because there's 4 column vectors. And each of those column vectors is in R3, so they have 3 entries, which means there are 3 rows in this matrix. Okay, so how many pivots could this matrix have at most? So there are, at this point, if you guys weren't able to get an answer before in terms of whether you guys were thinking yes to this problem or no, pause the video one more time for about 20 seconds, 30 seconds or so, and think about what's the most number of pivots a 3x4 matrix could have. Okay, so hopefully you guys did that. Well, let's talk about it. So in this case, because there are 3 rows, that means, so this matrix can have at most 3 pivots. At most 3 pivots. So in general, a matrix cannot have more pivots than it has rows, and there can't be more pivots than there are columns. So this particular matrix can't have more than 3 pivots, because that's how many rows it has. And it also can't have more than 4 pivots, because that's how many columns it has. But I never even reached the possibility of 4, because I sort of run into, like, I'm restricted by the number of rows first. So this matrix for sure cannot have more than 3 pivots, because it only has 3 rows. Okay, so as a result of that, not all the columns have pivots. Not all the columns have pivots. At least one column won't have a pivot. And that means that the column vectors are linearly dependent. So in terms of the answer to this question, the answer is, so the question was, can they be linearly independent? The answer is no. No matter what they are, there's not going to be a pivot in every single column. So the vectors for sure are linearly dependent. Okay, so the intuition behind this is, the reason why this is intuitively true is, there aren't 4 vectors. Better way to say this. There aren't 4 independent directions in R3. This question was asking about, can we have 4 vectors in R3 that are linearly independent? Conceptually, for that to happen, I need to be able to sort of construct 4 vectors that are in completely independent directions. And in R3, this is a 3-dimensional space, there are only 3 sort of independent directions. So we can generalize what we just observed in this example, and that's to note that if we had a matrix that had m rows and n columns, and there were more columns, so n is larger than m, there are more columns than rows, then the columns are always going to be linearly dependent. And the reason for that is, if there are more columns than there are rows, I can't have a pivot in every single column. I would have free variables. Okay, so let's look at another example. So this is a true or false question. So the statement is, if v1, v2, and v3 are elements of R3, and v1 is not a linear combination of v2 and v3, then the set of vectors v1, v2, and v3 is linearly independent. Okay, so at this point, I'd want you guys to pause the video, this time for about 3 minutes, and think about this one. So 4, 3, 2, 1, pause the video. Pause the video for about 3 minutes and think about this one. Okay, so hopefully you guys have done that. Hopefully you guys paused the video and thought about it. Okay, so the key thing that I want to use here is a theorem that we talked about in a previous video, which is, if I have a set of vectors, that set is linearly dependent if and only if at least one of the vectors, I'm just calling it vi, is a linear combination of the other vectors. And we pointed out before that with the statement, when it says at least one, we don't necessarily know which one. We don't necessarily know which one when this says at least one of the vectors is a linear combination of the others. So with that statement in mind, if I revisit our problem says that v1 is not a linear combination of the other two. But it doesn't say anything about v2 and v3 and whether they may or may not be linear combinations of the others. And that's the key thing that we want to try to exploit. So because our problem statement doesn't match up exactly with what this theorem is saying, there's a discrepancy, it's making me think that this is false, that we can find a counterexample. And it turns out it is false. But now let's give a counterexample, because my problem said, oh, if it's true, explain why. But if it's false, give a counterexample. So to give a counterexample, I need to give a specific example for what v1, v2, and v3 are that shows that this is false. Okay. So let's sort of recap what we need. To have a counterexample, I would need v1 to not be a linear combination of v2 and v3, but I would want my three vectors, v1, v2, and v3, to be linearly dependent. So to try to do that, I'm going to try to make v2, and v3 be sort of like dependent on each other. So what do I mean by that? I'm going to try to make them really, really simple. I'll just make v2 actually all zeros, just the zero vector. And I'll make v3 the same thing. The reason why that's nice is because now v2 and v3, they're actually just multiples of each other. So because of that, my set of vectors is definitely going to be linearly dependent. Okay, but I'm not done with my counterexample. I need to come up with v1. But v1 needs to not be a linear combination of v2 and v3. Okay, so what would v1 be? Well, I'm just taking, when I make a combination, linear combination of v2 and v3, I'm just taking linear combinations of the zero vector. So for v1, I have to pick something that's not the zero vector. So I'll just pick 1, 0, 0 for simplicity. And now let's check this. Let's check that if I form a linear combination of v2 and v3, so I have some number times v2 plus some number times v3, that I don't get v1. So if I do a times the zero vector plus b times the zero vector, well, that's just the zero vector. And that is not equal to v1. That is not equal to 1, 0, 0. So because of that, v1 is not a linear combination of v2 and v3. And that's one of the things that I wanted. Let's zoom out a bit. So one of the things that I need to show is, in my counterexample, that v1 is not a linear combination of v2 and v3. We've done that. And now what I need to do to show that it's false is show that this set is actually linearly dependent. Okay, so to do that, let's put these vectors as columns in a matrix and show that there isn't a pivot in every single column. So if So v1 is 1, 0, 0, and the other two vectors are just all zeros. That's the vector where that's the matrix where I've put all the vectors in as columns. So this matrix doesn't have pivots in each column. And as a result, that means that the column vectors, v1, v2, and v3, that set of vectors is linearly dependent. And that's what I needed to show to finish this statement off, to show that it is false. I have shown that the conclusion is false. So we've come up with a situation where the given portion of the statement holds, but the conclusion does not, and that shows that this is false.